We conclude our discussion of simple harmonic motion before we move on to wave motion with a discussion of forced oscillations and how they can cause a condition called resonance. Now, objects have a natural vibrational frequency, sometimes many natural vibrational frequencies depending on the object. It's a frequency at which a system would oscillate if there were no driving force and no damping force. So, for example, a simple pendulum, the equation we looked at when we talked about a simple pendulum would be the natural frequency, calculate the period of the pendulum and then take the inverse of that to get the frequency. That would be the natural frequency of that pendulum. That's the frequency at which that pendulum wants to oscillate. For example, going out to a school, using a swing as an example, when you swing on a swing, depending on the length of the chain, right, this is a simple pendulum, depending on the length of the chain and local gravitational pull, which doesn't change over the surface of the Earth, you'll get a different period for each swing, but that swing will have a natural frequency, a frequency at which it wants to oscillate. Now, if you add a driving force to that system, now a driving force is an outside force, periodic outside force, that places energy into the system. If you've ever been pushed on a swing as a child, or pushed someone on a swing, then you know about driving force, right? You are outside of that swinging system, adding energy every time you push the person on the swing. You are an outside driving force. It's periodic because, ideally, whenever the swing comes back, you give it a shove. That's a driving force. It's an outside force adding energy to the system. Without you, your child would just basically hang there on the swing, or your friend would hang there on the swing. Yes, you can kick yourself and get the swing moving, but we're going to talk about just someone pushing. Now, how you apply the driving force matters if you want to have fun on a swing, right? If I'm providing a driving force, it's a periodic force, but it doesn't say what the period is. Let's say the period is once every 5 minutes, right? Or the frequency is once every 5 minutes. So the period is 5 minutes. So I come by every 5 minutes and give you a shove, and then walk away. And I come back 5 minutes later and give you a shove and walk away. That's not really going to do much on the swing, right? The damped motion will definitely die out before you come and push me again. Or let's do the opposite. Let's say I push you 10 times a second, right? Just go behind you, push, 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 that fast, or even faster. Again, that's not going to do much. It'll mostly be annoying. In order to really get the swing moving, you have to have a driving force that's near or at the natural frequency. And we all do this intuitively when we push someone on a swing, right? We push, they go forward, they come back, and when they come back, we give them another push. They go forward, they come back, we give them another push. Every time we push, our pushing is at the same frequency as their motion. What happens is when the driving force is near the natural frequency, a condition called resonance occurs. Resonance is the rapid increase in amplitude caused by a driving force near the natural frequency of the object. This can be good or bad. In the case of swings, it's good, right? You want to get higher and higher quickly when you're on a swing. So pushing at the driving force is appropriate, or the driving frequency is appropriate. And there are some bad things. There was an earthquake near Mexico City. Mexico City has various high buildings. Right? You have short buildings, medium buildings, and tall buildings. Well, each building has a length associated, right? You can think of these as reverse pendulums. They're attached on the ground, and they're allowed to sway back and forth at the top. Right? There's nothing holding the top at a fixed position. Now, wind can cause a building to sway a little bit, and we talked about that damped motion trying to prevent that. But now let's imagine an earthquake where the entire ground is violently shifted back and forth. Violently shifted back and forth during an earthquake. Well, that earthquake is a driving force. each of these buildings has a natural frequency of oscillation depending on the height of the building. A few other things as well, the mass distribution. But we're treating these as inverse simple pendulums, that it's just the length that matters. Really bad assumption, but bear with me. So each of these buildings has some natural frequency, we'll say F1, F2, and F3. If the frequency of the earthquake, let's say F2, is close to the natural frequency of mid-sized buildings, then mid-sized buildings undergo resonance in that their shaking amplitude gets bigger and bigger and bigger with each push from the earthquake. And in Mexico City, this happened over a decade ago now, where the mid-sized buildings, which were close to the natural frequency of the earthquake, all toppled. The taller buildings, which had a natural frequency further away from the driving frequency, stayed up, and the smaller buildings stayed up. So this frequency was probably too short. This frequency is probably too large. So middle buildings ended up getting the brunt of the energy. And of course, if you increase the amplitude dramatically, the energy depends upon the amplitude of oscillation, so you rapidly increase the energy. If you've ever seen the famous opera singer shattering a wine glass or a crystalline glass, a glass has a natural frequency. If you've ever taken, dip some water in a glass and run your finger around the lip and you hear the vibration, you hear that note it creates, that's the natural frequency of that glass. You can change that by adding water and things like that, making different notes, but it is the natural frequency of the glass. So if you provide an outside driving force, like a powerful opera singer's voice, at that frequency, that causes the glass to vibrate in resonance and can cause the glass to shatter. Now, it's much easier to do that with equipment, sending a signal at a very specific frequency, but supposedly, famous opera singers with powerful voices can do the same thing. Hit that note perfectly, and the resonance, the driving force creates a resonance in the glass, which can shatter the glass.